Okay, so there were a couple of things that popped up on the exam that were sort of common issues that I just wanted to address real quick. So let me go back and look at this. Let's see. For number one, I loved all the different approaches people took to number one. I think it's just easiest if you use the variation of parameters, because the Wronskian is pretty easy. It's just an e to the -4, but regardless, that one went pretty well. For number two, the biggest issue with number two, twofold. One was getting the correct K value, because I gave you a mass, but for K, you need the force. So you actually have to multiply it by the gravitational constant. So that gives you a K of 1,000. And then the other issue, and I don't think anybody did this, nobody found the C1 and C2. You all left it. And there was a key phrase in there that says that the spring mass system is disturbed from equilibrium by the force of 20 e to the -t. So that actually tells you that both y of 0 and y prime of 0 are 0. Okay, because it's initially at equilibrium and then that force gets applied. So that was the other pretty common thing that happened on number two. Number three, a couple things for this one. Most people saw for the polynomial bit, you need a third degree. For the cosine and the sine, each of those needs a linear bit to it, since we had an x cosine of x. So it's not enough just to have a, like an ax cosine of x. You also need a b cosine of x. And the same thing for the sine. So that one ends up giving you 4 different coefficients that you need. And then for the e to the 2x, so that one, it was an x squared e to the 2x, which would suggest needing some sort of a ax squared plus bx plus c times e to the 2x. Well, the problem is that 2 of those are in your fundamental set. And so you need to multiply until you no longer have any of those. And so you need to multiply by an x squared so that you get an x to the 4th, an x cubed, and an x squared times e to the 2x. So a couple of little things on that guy. Number 4 went pretty well in general. Mostly it was sign errors. And a couple things just to watch out for. Sometimes you can incorporate some of those particular solution bits into your fundamental set. Like that happened in 4. A lot of people ended up with a 1/3 x squared. And that can actually get combined into the C1 x squared. I didn't take points off for that. I probably made the comment. So if you ever saw that, like, you don't need this, it can be part of the fundamental set or something like that. That's what that meant. So number 5, most people did fine finding the fundamental set, the e to the -4000t and the e to the -1000t. But the issue there is that that battery, that 12 volts, that actually isn't, that's not an initial condition. That's actually the forcing function. So when you have that thing set up, it's q double prime plus 5,000 q prime plus 4 million q equals 12. So that then changes your solution, because not only do you have the fundamental set from the homogeneous, but you have to add on, I think it's like 3 times 10 to the -6 or something like that, which then kind of led to problems. So there was that. And then what I asked for was the current, and the current is actually q prime. So for those of you that just gave me a q equals, you got to do that next step, which is find the q prime. So number 6, I know some of you made nice little comments about, how horrible this was with all of the coefficients and everything, but it turns out you can break it down pretty easily. For the sine bit, just make an a cosine and a b sine, and it falls out pretty fast that b is -1/2, a is 3/2. For the e to the 3t, you actually need a t e to the 3t. Again, for the same reason as whatever that one was with the big long one, because of the fact that e to the 3t is part of your fundamental set. So that's just one piece, just ct, e to the 3t. And then you'd go to the linear bit, so that t suggests having a linear, but you actually have to bump that up by multiplying by t, because 1 is in your fundamental set. That's what you get for r equals 0. So that should be a dt squared plus et, something like that. So really, there are only 5 unknowns. And it's not like you get a system of 5 unknowns, because the a and b just go together. The c, it falls right out. And then d and e are pretty quick when you just look at the polynomial piece. So anyway, beyond that, the other issues were really just algebra issues, arithmetic issues along the way, finding your c's. So, and then number 7, again, it was like sign errors, but the one fundamental thing that happened quite a bit was in calculating the mu, the drag coefficient. Many of you just put in 35, but the 35, that was the force. It was a drag force. And you find mu by dividing by the velocity. So that should really be a 7, because we had a force of 35 newtons when it was going 5 meters per second. So obviously, if you change that number, everything else falls, it gets really crazy. The one other thing I want to mention is that for this one, when we pulled it down, that's actually a positive initial condition, because the way that we've got that equation set up, with the m times y double prime plus mu y prime plus ky, we developed that with positive being down. So if you're going to use that form of the differential equation, make sure your initial condition is positive. The only difference, you end up with an opposite. You get negatives, which in a real situation would still be okay, right? Because like you could say, oh, I got a negative, but negative was down. But technically, and that worked out for this one, not always, but technically you should still go down as positive. All right, wait a minute. So that's pretty much what happened on the exam, but overall pretty well. In general, I was pretty pleased with what happened. Just a lot of little things that added up. So for those of you that were getting like scores like 88s and stuff like that, those easily could have been A's with just a couple of minor tweaks. So anyway, so before we go into other new stuff, any questions on that exam? Hopefully my comments made sense on your paper. All right, so how about homework? Anything from the chapter 8 stuff that we want to look at? How's Laplace transforms going?
They're good. I'm starting on the 8.4, 8.5 stuff earlier today. I haven't got to the assignment yet, but I was going through the book. It's I was watching your video from Monday, and it seemed a little easier than the way the book explained it. So
yeah, and step functions, it's just, I mean, they are what they are. They obviously make things uglier. Like I don't know if you got to the point where I had to turn the board sideways and still use 2 lines to write out one of the solutions. But in terms of the structure, they're pretty straightforward. So I'm glad to hear that so far, no big deal. Everyone else good? Homework-wise? Or are we at that, like you're talking about this is one of those things where you're just like, meh, at this point?
Well,
meh. You don't have to answer that.
No. It's like, yeah. I mean, everything pretty much made sense with all the Laplace transforms and whatnot. It's just, slugging it out with the partial fractions. So,
yeah.
I hope it's all right if we use Symbolab to do partial fractions, because there's a lot of that crap.
Yeah, that I'm absolutely fine with that.
Cool.
I don't mind you guys using Symbolab as a tool.
Yeah, I mean, it's just an intermediary step that you should already know, and we're not really technically being tested on.
Right. Exactly. You know, I want to see that you know how to do the differential equation stuff. I want to see that you can recognize once you're in that partial fraction form what the original functions were and stuff like that, you know. Because I know Symbol Lab, like you can just type in a differential equation and it spits out the answer, right? And it even shows you steps and all that. That I don't want, obviously. But yeah, if you want to do the partial fractions, have at it. Same thing, like you get a system of equations, like from the undetermined coefficients. Absolutely, put it into a matrix and let something do it for you, right? Like that's kind of the point of having done all of that before now. So, all right, well then I guess we're going to go ahead and move into chapter 9. Now, chapter 9 is going to go really fast. It's going to go really fast because what we're going to do is we're going to turn our attention to higher order differential equations. So things that now have third derivatives, fourth derivatives, nth derivatives. And the reason this is going to go fast is that nothing has really changed. We still use the same processes. We still do the same things. We just have to expand it a bit because they're higher order. Okay, so expect this one to go kind of quick. You'll notice that when I had this set up, I had it as 2 days worth, and I think that's probably going to be about right. So let's take a look at this and see what happens now that we go higher order. So I'm going to go ahead and go to the whiteboard real quick. All right, so higher order. Just like it sounds, this just means that we've got derivatives that are bigger than second derivatives. And so what we're going to do, we're going to generically say, we're going to have something of the form that's P naught times y to the n plus P1 times, that's not y to the n, the nth derivative, n minus first derivative plus so on down the line until we get plus Pn minus 1 times y prime plus Pn times y. So this is how we're going to do it generically so that we all kind of have the same, or we can do this for any kind of order. So we'll have the P0 through Pn. Those are the functions that are multiplying to our y's, our derivatives. And then, of course, this is going to equal something. And let's just call it g of t. So we got some function at the end. All right. So what's different about these as opposed to the other ones? Well, obviously, our terminology is the same. So if we're talking about a homogeneous, it's equal to 0. Non-homogeneous, g of t is whatever. And we still want to have a fundamental set. We still want to talk about particular solutions, you know, so like all of this stuff, it's the same terminology. But here's what's different. All right, so first of all, in terms of the fundamental set, it's actually going to be made up of n linearly independent functions. So we've actually seen that so far. You think about the first orders. We always had just one function we were multiplying by a c. We've been in second order world for quite some time, but we've seen that there are 2 functions. Now we're just going to have n of them. So the fundamental set is just bigger. So in essence, what we've done is we've increased the dimension of the space, of the solution space. And that dimension always matches the order of the differential equation. Okay, so that's really the first big difference. And it's important, but what's kind of nice is you know how far you have to go. You need to make sure that you find the same number of fundamental set in the fundamental set as the highest order here. And so it's kind of cool. It's like the measuring tape lets you know when you're done. Okay, so we're now going to have y1, y2, all the way down to yn, which means the solution to the homogeneous, and I'm just going to put here a y sub h. You know, we write the sub p for particular. I'll do this for homogeneous. Well, it's just going to be a linear combination of those. So now we're going to have C1Y1 all the way through CNY. All right, so this is the big difference there in terms of the homogeneous. Now, if we're talking about a non-homogeneous, where this is equal to G of T, we're still going to have the same deal, where y is going to be the sum of this with a particular solution. And I don't know if you remember, we did develop kind of this idea for the second order, how we could solve the homogeneous and then add on a particular. Well, the way that we derived that had nothing to do with the fact that it was second order. It could have been 300th order and the same logic would have applied. So that's kind of good. We don't have to do something new here. We realized that finding the homogeneous is going to take longer potentially because we have more functions that we have to find. But as long as we can find a particular, we'll be good to go. Okay, so there's a little bit of a difference here, but at least in terms of finding our solution, it looks exactly the same. Okay, so some other things that we might want to consider, because we saw that they were useful. How about things like the Wronskian? So you remember the Wronskian, hopefully, because we saw that it was kind of useful. And we created it using the y1 and the y2. Well, now, if we've got n functions, then this Wronskian matrix is going to have in it y1, y2, all the way down to yn. So it's going to have n columns. And then in each of the columns, again, we take derivatives. So it'll be y1 prime, y1 double prime. And we're going to keep going all the way until we get to the n minus first derivative. So just like with the second orders, remember the furthest we went was just the first derivative. So this is kind of cool because, again, this isn't new. It's exactly the same idea. It's just bigger. And we still want to find the determinant of this matrix because that will give us our Wronskian. You can use that to determine whether or not they actually form a fundamental set, right? See if that determinant is 0 or not. And all the other things the Wronskian did for us. Well, now if we want the Wronskian, it's just from a bigger matrix. So related to that was Abel's theorem. So let me remind you the second order version of Abel's theorem. Let me put here for second order. What we saw was that the Wronskian, so the determinant of this matrix, was some multiple of e to the negative integral of p dt. And usually we just use the 1 on the k was sufficient, right? So we don't necessarily know exactly the Wronskian, but we know it at least off by a scalar multiple. Okay, so that was the second order version. I know that you guys probably don't see the power of this or how useful it is, but it can be a faster way of finding that Wronskian so that when you are making use of it, excuse me, it's gonna be a little bit quicker. It wasn't that big of a deal for a 2x2 matrix, but imagine that we're talking about a 20x20 matrix, and I want you to find the determinant of that. even using technology, we don't really want to do that, right? I mean, just entering that sucker in is going to take forever. So if we had a way of using Abel's theorem, it'd be much better. And so there is, and it's this. So if we go to higher order, I just realized I wrote this like second with the higher, up higher. It's that point in the quarter. I'm getting a little punchy. Okay, so for higher order, again, we know that Wronskian is going to take on the same kind of form, but now instead of P, it's going to be P1 divided by P naught. So remember that P naught, that's the function that's in front of or being multiplied to the highest derivative. And then the P1 is your next one. And if we go to second order, it actually, that's exactly this, because you may remember that the P was found by writing it as just y double prime equals. Right? So this is kind of cool. It makes it so that we can figure out, at least within a constant multiple, the Wronskian, even if we're in the situation where we've got a crap ton of functions. All right, so very similar, but very faster. All right, so let me show you an example. Let me give you a differential equation where we can actually figure out what the Wronskian is without bothering to find the entire fundamental set. So let's just take this guy. We'll make it nice and easy. We won't even make it so that the functions are all crazy or anything. But let's say we've got fourth derivative of y plus 2y double prime plus y equals 0. All right, so this would have 4 functions in its fundamental set. All right, that's because of the fourth derivative here. So we would have a 4x4 matrix if we wanted to actually calculate the Wronskian. Okay, well, instead, what we can do is we know the Wronskian is going to be some scalar multiple of e to the negative integral of P1 over P naught. So P naught is 1, because we've got 1 fourth derivative of y. So what's P1? Be careful here. Because remember, P1 is the next one in our list, right? We have P naught times the nth derivative plus P1 times the n minus first derivative plus P2 times plus P3 plus P4. So P1 is the next one, but the next one here would be the multiple on the third derivative. And the multiple on the third derivative is actually 0. So it's pretty easy to fall into, oh, that should be a 2, but it's not, because there's actually 1 in between. Okay, so
it was
integrating
0.
0, of course, 0. So we get k times e to the 0, which is k. So it turns out that the Wronskian for this differential equation is going to be a constant. We just don't know what constant it is. But again, think about places where we've used the Wronskian. It might be nice if all we're doing is dividing by a constant. Even if it's unknown, that can get lumped into other unknown constants and the like, right? So Abel's theorem can be really, really fast in this case. All right, so in terms of the theory, these things behave exactly the same as second order. And that's because second order are a special case of higher orders. You can actually prove all the things that we did for second orders. Like, remember the existence and uniqueness theorems? where you look at, are these p's continuous and differentiable, and are their partials continuous and all that. You can do the same thing. And in terms of where you're guaranteed a solution to an initial value problem, are all of the places, all of the intervals where every one of the p's is continuous and where every one of the partials is continuous. And so what we had to do before was really just check two functions, because in this naming scheme, there was a P1 and a P2. Well, now we have to do P1, P2, all the way through Pn. Okay, so like all of the theory is exactly the same. So let's turn our attention to actually solving these. How do we go about finding solutions to these higher order derivatives? Well, we're going to kind of follow the same progression we did last time. Let's start with homogeneous, and then we'll go to particular, or non-homogeneous. I mean, obviously, we still need to know the homogeneous to get the non-homogeneous solution. So let's start with homogeneous, and let's start with constant coefficients, like the one that I just wrote. Okay, so the question is, how do we go about solving this? Well, let's think back. How did you go about solving this kind of thing when it was second order?
Didn't we look at try and find the well, find the general solution by creating a polynomial?
Okay,
Based
we
on
did.
yeah.
We created a polynomial. And where'd that polynomial come from?
It came from the power and coefficient of each of the differential chunks.
Okay, so we saw that we could just write this, like in this case, the translation would be r to the fourth plus 2r squared plus 1.
Yep.
Right? Okay. But where did this polynomial come from? Do you guys remember how we even started by creating those? This is really good review for class, because that was like 2 months ago, maybe a month and a half ago. Well, where this came from, we made a guess. We just said, hey, let's try e to the r. And the rationale behind that was that when we differentiate an exponential, we get another exponential. And so we're going to get a string of exponentials that we're now adding. And when we made this guess, right, y prime was r e to the r, y double prime is r squared e to the r. If we continue that, we're going to get r cubed e to the r, and so on, so that the nth derivative is going to be r to the n times e to the r. And so that's why we were able to just replace any of those powers or any of those derivatives with r's to that same power, because you notice how those always match up. And I just wanted to show you this to affirm that we can do the same thing. We can actually go through the exact same steps that we did for second order. So basically what we're going to do is we're going to create the polynomial. And then once we've got that polynomial, we find all of its roots. And those roots tell us what the fundamental set is going to look like. All right, so let's try this one. So we got a fourth order. Oh man, we've never done anything like that before. But let's kind of follow this process. So we make this polynomial. Maybe you see that this factors. It actually factors as r squared plus 1 times r squared plus 1. And so in terms of roots, this one's going to give us plus or minus I, because r squared has to equal -1. And we actually get the same thing for the other. So let's see if we can create our 4 functions that are part of the fundamental set. All right, so plus I and minus I, that tells us that one of them needs to be cosine of t, and the second one needs to be sine of t. Right? If this had just been a second order and you get r of plus and minus 1, you go boom, those are my 2 functions. So those are still going to be part of the set. All right, now we look at the other one, and we see that we get plus or minus I again. All right, well, what does that make you think?
Tack on a t.
Yeah, before we had to end up multiplying by a t. Well, that's exactly what we're going to do here. So y3 is going to be t cosine of t, and y4 is going to be t sine of t. So the solution to this differential equation, since it's not an initial value problem, is going to be c1 cosine of t plus c2 sine of t plus c3 t cosine of t plus c4 t sine of t. And so this is what I was saying in terms of the nothing changes, because we still do exactly the same thing that we did before. We just have more. So creating this fundamental set is just going to take longer because we have to find all of the solutions. All right, let's try another one. We'll do like 2 more of these, and then we'll make them non-homogeneous. All right, so here's another one. Let's go with the 6th derivative of y minus the 2nd derivative of y equals 0. All right, so start by making a polynomial. What's it going to look like in this case?
R to the 6 minus r squared equals 0.
Okay, so it's going to be r to the 6 minus r squared. All right, now let's go and see if we can find those solutions. So we'll factor out an r squared. So that gives us r squared times r to the 4th minus 1. The r to the 4th minus 1, that's a difference of squares. So that'll be r squared times r squared plus 1 times r squared minus 1. And the r squared minus 1, we can even go further still. That factors to r minus 1 and r plus 1. All right, so that's as far as we can go factoring. So let's start writing out what our r's are. So we've got an r of minus 1 and an r of plus 1 from those last two. The r squared plus 1, that gives us r equals plus or minus I. And then r squared, that's going to give us an r of 0. But that r of 0 is repeated. So it's really important to keep track of your multiplicity. So let's just write that here. Let's not forget that this is multiplicity of 2. So there are the 6 roots. -1, 1, I, negative I, 0, and 0. All right, well, let's create our fundamental set. So we'll just start with 0. So that tells me that y1 is equal to 1. So e to the 0. The second 0 tells me I need to multiply that by t. So t is also a fundamental in the fundamental set. All right, then we get I. Well, the plus and minus I give us y3 and y4. So those will be cosine of t and sine of t. So then lastly, 1 and minus 1. Well, the 1, that's going to give us an e to the 1t. And the minus 1 gives us e to the minus 1t. So you take a linear combination of those 6, and that's your generic solution to this differential equation. All right, so are you okay with my statement of these aren't that big of a deal? It's really just the same thing, just more. So what's going to make these complicated is really, what does this polynomial look like? Right? How bad is that to factor, to find solutions to? But this is also one of those places where you can feel free to use like Symbolab or something like that. I'm going to guess that Symbolab finds you solutions to equations like this. I would be shocked if it didn't, but this would be perfectly fine if you wanted to go, okay, well, I just created this 6-degree polynomial. Have at it, Symbolab, find me the roots, right? But again, it's an algebra question. Once we got our roots, we can find our functions. Okay, so I told you we were going to do 2 more. The next one I want to do an initial value problem. Because initial value problems, there's a bit of a twist to this as well. Think back to initial value problems you did before. How many initial conditions did you need?
It depended on what the power of the differential equation was.
That's absolutely true. It depended on the order. Because when it was linear, or sorry, first order, you only needed to know something about the function. For the second order, we needed to know something about the function and its derivative. We actually needed 2 bits of information to get the 2 different c's. Okay, well, if we think about it that way, if I had an initial value problem here, I'm going to have to find 6 different coefficients, which means I'm going to need 6 different pieces of information. And so as soon as we go to an initial value problem with these higher order, each bump in order requires 1 more thing to be known. Okay, so let me just write this. So for a higher order initial value problem, you need n conditions. But other than that, nothing is different. We still go about it the same way. We still find our solutions the same way. It's just there's more information that needs to be known. So you know how when we have these, we write the differential equation and then it's usually like an afterthought. Oh, y of 0 is 1 and y prime is 0. Well, that now afterthought can be a huge list. Like the one we just did would require 6 initial conditions. So those lists can get awfully long, but in terms of the process and what we do, there is no difference. So let me give you one. This is what they're going to look like. So let's say we've got a differential equation where we've got the 4th derivative minus 4 times the 3rd derivative plus 4 times the 2nd derivative is equal to 0. And now we're going to have 4 pieces of information. So maybe we'd have, say, y of 1 equals minus 1. Y prime of 1 is equal to 2. Y double prime of 1 is equal to 0. y triple prime of 1, let's say, also equals 0 or something like that. So again, notice that there are 4 pieces of information, and it usually is something about your function, its derivative, second derivative, and so on down the line until you've hit the last one that you need, which is always the n minus first derivative. Okay, so that's how these change, but in terms of the process, it's exactly what we did before. So let's start by creating our polynomial. So it's going to be r to the 4th minus 4r cubed plus 4r squared equals 0. We can factor out an r squared. So we've got r squared times r squared minus 4r plus 4, which then that also factors to r minus 2 squared. Okay, so here's our general form. We've got a root of 0 that appears twice. So that means we're going to get a C1 plus a C2 times t. We also then get a root of 2 that appears twice. So we're going to get a C3 e to the 2t plus a C4 times t e to the 2t. And I think what I want to do is we'll just get to as far as the system of equations. Let's not worry about actually finding the c's, but at least get it set up. So now we'll use our initial conditions. So like if we look at the first one, we're told y of 1 equals minus 1. So that'll give us minus 1 equals C1 plus C2 plus C3 times e squared plus C4 times e squared. Okay, so now let's go to our derivative. So y prime is going to be C2 plus 2C3 e to the 2t plus C4 e to the 2t plus 2 C4t e to the 2t. So product rule on that piece. So the derivative equaling 2, well, that'll give us 2 equals C2 plus 2C3 e squared plus C4 e squared plus 2 C4 e squared, or sorry, not e to the 2t. And I'm bored. I think you're probably bored too. So we're going to get 2 more 0 equals that come from the second derivative and the third derivative. Yay raw, we find our c's. Okay, so the initial value problem, they're longer now. You're going to get bigger systems that you have to solve. But in terms of the process, it's identical. And by this point, you guys have done enough math that you should see that it's the process that we care about. The rest is details, right? The rest is symbol lab. If you can ever get to the point where you're like, nah, can I just put it in the symbol lab and do my thing? Okay, that's enough. And what we're seeing here is that to get to what you put into symbol lab, we do it the same way. All right, so how are we feeling with these constant coefficient homogeneous types?
It's pretty straightforward.
All right, good. I'm glad you think that, because I agree. I think it's just more of the same. It's just every time we bump up that order, you're going to start really hating fourth derivatives. You're going to hate them, because as soon as you see one, you're going to go, shit. Now I'm going to have a 4x4 system. Everything I do is 4x4. Blech. We don't like 4x4 determinants. We don't like 4x4 anything. 3x3s are still not that bad. Third derivatives, you'll tolerate. But fourth and higher, they suck. They suck because it makes the work that much harder. But it's only harder because it's more, not because it's different. It's just you got to do more of it, right? Think of it like plowing a field. Plowing a field is plowing a field. It's a little bit different if you plow 1 acre than 100 acres, right? And that's what's going on here. We're still plowing. It's just the field got a bit bigger. All right. So, yay, no big deal. So what about the non-homogeneous? Now, we already have seen, or at least I already kind of talked about the theory, that the solution to a non-homogeneous still has the homogeneous in it, right? We're still going to take that homogeneous solution, but now we're going to add on a particular solution. So the question is, how are we going to find this? Because we already talked about the homogeneous, at least with these constant coefficients. So what do we do about finding a particular? Well, what did we do before? When it was a second order, but it was some second order equals a non-zero function, what did we do? And just FYI, the answer to that question is long, because there are lots of things we did. But what were some of the things that we did?
There's there's a lot of ways to deal with it depending on which situation you're presented with.
Yeah, it really came down to what was that f equal to, right? If we've got whatever our differential equation equaling, say, f of t. Okay, so we have our generic differential equation equals f of t. We saw that the approach really kind of depended on the f of t, but also a little bit about like the fundamental set, right? And so in terms of things that we did to help us do this before, we did things like undetermined coefficients. So undetermined coefficients, that was the make a guess of the form. So if it looked like, if it was a trig, we put in trig. If it was a polynomial, we put in a polynomial. If it was exponential, we put in an exponential or combinations thereof. Multiplying by t's or t squared or t cubed or whatever in order to make sure that we don't have overlap. Right? So undetermined coefficients was one of the things that we did. Another thing that we did was reduction of order. Do you remember what we needed in order for us to do reduction of order?
Didn't we need to know one of the solutions?
Yes, we need to know one of the fundamental set. So if we had an element of the fundamental set, then we could use that and make a guess for the next one, which would be some u times that guy. And basically what it did was it reduced the order. All right, so we can still do that. But again, like Thea said, it requires that we know one of the fundamental set. In fact, the more of the fundamental set you know, the better that is when it comes to doing a reduction of order, because each one of them lets you bring it down by one. But that should also kind of make sense, right? Because if we're creating a n-dimensional space, we need n functions. And if we already know two of them, okay, now we're down to an n minus 2 that we have to fill in. So we've reduced the order. It's like having an n minus 2 differential equation. Okay, so we did reduction of order. Another one that we did was variation of parameters. And variation of parameters, that was the one where we made the matrix, the Wronskian, and we used kind of the determinant of that. We set some conditions so that all we needed was its determinant, and then that helped us find the two solutions, right? Where you take, well, remember what you did? You take your y1 times the g, and then divide by the Wronskian, and then integrate, and right. So that there, it was kind of nice because there was a very specific way of doing it. So these were like the three big things we did when it was second order. So what are we going to do when it's higher order? These three things. These exact three things, because higher order doesn't really change anything. Think about undetermined coefficients. So if I gave you a polynomial as my f of t, it's real natural to go, okay, I must have a polynomial that I start with. And we already know that derivatives of polynomials are polynomials. And it doesn't matter how far I go down by differentiation, I'm still going to get a polynomial. Think about sine and cosine. If we had a sine or a cosine, we put sine and cosine in there because they showed up in the derivatives. Well, they show up in the derivatives forever. Same thing with exponential, right? With the exponential, we put in exponential guesses because exponentials give us more exponentials as we differentiated. And the same thing's going to happen if we take a 20th derivative as opposed to a second derivative. So the rationale behind what we did for undetermined coefficients still definitely applies. So, all right, so what? So it's a sixth order differential equation, no biggie. I mean, it's going to suck because we're going to have to take 6 derivatives and everything when we want to find out those coefficients. But this gets back to that, it's just more. We're doing the same thing, it's just more because n is bigger. Okay, so it definitely makes sense that we should still be able to do the undetermined coefficients. So what about reduction of order? So what was the rationale behind that?
If you're able to find some of the set, you can easily do it, but
yeah, like given an element in the fundamental set, you can put in a multiple of it. And we saw again by the structure, if you take u times a fundamental set, when you put that into the differential equation, it doesn't matter what it was, it made the constant function, the non-derivative part, go away. So then we could replace, you know, z equals u prime or whatever, and then go. Okay, well, that theory was independent of the order. Didn't matter. You're always going to lose that constant term, which means if you replace in a z equals u prime or whatever, you're now one, your order is one less than what you started with. Okay, so in terms of, can we do that again here? Sure. Nothing about the theory behind that required second order. So basically reduction order will take a third order and make it a second. It'll take a fifth and make it a fourth, and so on. And so if we can continue that process, if we can continue to find more, we can keep knocking down that order until we get to something that we can deal with, right? Like if we can get to second order, we're good. Because we've already seen, we know we're for sure at second order. But anyway, so can we do reduction of order again? Absolutely. It's just as valid. It's just to go all the way, we're going to need to know more. Like really, reduction of order is perfect if you know all but one. And when I'm saying all but one, I mean all but one of the solutions. that are in the fundamental set. So if you've got all but one of them, beauty, you're done. Do reduction of order and you got the last one. But it's still useful if you have any of them, right? Because I think it's pretty clear that if instead of having a sixth order, I could have a fifth order, I want the fifth order, right? Okay, so that was reduction of order. And then variation of parameters. What did we need to do variation of parameters? And if you don't know it by that name, that was the create the Wronskian matrix and then go through the process to find our solutions. So do you remember what we needed to do this?
To slug it out through the derivatives, or do we need to know? Yeah.
So we did have to worry about finding the derivatives of everything. But kind of where I'm going is we needed to know the entirety of the fundamental set. Because the columns of that matrix were formed by the different elements of the fundamental set, right? The top row was that function, and then we go down, we find the derivative. Okay, well, what we're going to do when we do this is then continue down to the second derivative and the third derivative and the fourth derivative. But kind of important here for variation of parameters is you need all of them. And this is the same them as the one, right? You need to know all of the fundamental set. So without the entire fundamental set, you can't really do variation of parameters. Okay, well, you already saw that it mattered what we had in terms of which these we could do. When it comes to the higher order, it's the same thing. You're going to start by looking at what do I know? Can I find the entire fundamental set? If so, variation of parameters starts rising to the top. Is the f of t a nice form? Okay, well then I can do undetermined coefficients. Do I know any of the fundamental set, but not all of it? That's where we jump into reduction of order. So you're going to use the same thought process in terms of which to do by looking at what you know. Now, in a situation where we've got this differential equation is one of those with just the constant coefficients, there we're going to know the entirety because we can create the polynomial and go. But it's going to be those that have weird multiples on the derivatives. When we're taking, say, x squared times y triple prime, those are the ones that are going to require 2 and 3 if we can somehow find fundamental sets. But that prospect is also going to be a little bit worse. Just think about second order, because here are your options. You can know all of them, meaning 2. You can know only 1, or you can know none of them. Okay, well, if you knew all of them, you're good. Variation of parameters will take care of you. Or undetermined coefficients if there's a nice form. If you know one of them, you're still good because you could do reduction of order. If you know none of them, well, then you're kind of toast. Okay, so, but now if you look at these higher order, you need to know all of them. Oof, that's going to be hard, right? Fifth order, we need to know all 5. So anything that requires all of them starts to disappear. And we're left with the other things, the reduction of order, right? So just realize that that is the one major complication, is that primarily you're going to fall into trying to do reduction of order and really hope and pray that whatever that new differential equation is one that you can figure out a solution to. Because as long as you can figure out one solution to the fundamental set, then you can do reduction order again. And then again, pray that you can find one, and so on. Okay, well, I feel like I've been preaching to you a lot, but hopefully I've beaten into you that this is no different. It's just more. So with that said, let's try a couple of undetermined coefficients. And let's see how we vary things, how we're going to change things differently, so that we can do this method. So we're going to stick with things that have constant coefficients so that we can find all of the fundamental set. And that also is going to make it so that it's a little bit easier for us to do this undetermined coefficients method. But let's try this. So we're just going to go up in order by 1. So let's take y triple prime minus 3y double prime plus 3y prime minus y. But now, let's make it equal 4e to the t. So we're going to stick with nice forms for right now, right? Obviously, undetermined coefficients. We're going to either have exponentials, polynomials, or trig, or some combination of those. But let's just start here. So just remind yourself the process. Go back in time. All right. Let's start by finding a fundamental set. So the fundamental set here, if we make our polynomial, we're going to get r cubed minus 3r squared plus 3r minus 1. And we need to find the roots to that. So I don't know if anybody recognizes that. This is usually where those of you who've been tutoring algebra have like a huge advantage over the others, because you run into these kind of things in the lower level classes. This is actually r minus 1 cubed. Those coefficients, 1, 3, 3, 1. That's the fourth row of Pascal's triangle. So that should be a trigger. If it's not, don't worry about it. But this is r minus 1 cubed, or use symbol lab or whatever. So here we get r equals 1, but it's got multiplicity 3. So the multiplicity of 3 then tells me that this is my fundamental set. y1 is e to the t. y2 is t e to the t. And y3 is t squared e to the t. So this is something else that's going to pop up, is sometimes you just got to keep multiplying by t. And so it's quite possible that you can get a t to the 4th times something. It really just depends on the multiplicity. All right, so that's enough for us to have the homogeneous. So we know what that's going to look like. So let's go and find the particular solution. So what kind of guess do we want to make for our particular solution? Since this is exponential, what do we want?
Exponential also, but it's going to have to differ, because if we tried to guess what exactly it is, it's already a part of the fundamental set. So
yep, you're right. So we would want to try ae to the t, just from the 4e to the t, right? We want something exponential. But this is where we look at the solutions to the homogeneous and go, well, crap, that's already in there. And so is t e to the t, and so is t squared e to the t. So what do we need to multiply to this?
t cubed.
T cubed. So I don't know if you remember when I talked about this before, it was like really quickly in passing, because we only ever had to multiply by t, right? Well, I guess t squared could have been the worst case. But what you want to do when you've got things that are in the fundamental set you want to multiply by t to the n, where n is the multiplicity of that root. So since 1 had multiplicity 3, we need to multiply by t cubed. Or alternatively, think of it as you need to multiply by whatever so that this original guess no longer has pieces that are in the fundamental set. All right, so there would be our particular guess. All right, well, let's see if we can use that to figure out what A is. So we need some derivatives. So the derivative of this particular is going to be A e to the t times t cubed plus 3at squared times e to the t. So product rule. So we'll go to the second derivative. Okay, well, we're going to get a e to the t times t cubed plus 3a e to the t times t squared plus, differentiating this, we get 3a e to the t squared plus 6at e to the t. Okay, well then we got to do one more. So the third derivative, we're going to get a e to the t times t cubed again. And then this piece, there's actually 6a of those. So we're going to get 6a e to the t times t squared plus 12a e to the t times t. And then this piece is going to give us another 12a e to the t times t plus 6a e to the t. All right, so let's put that into our differential equation. So the third derivative, it's a t cubed e to the t plus, now we're going to get 18. No, I'm sorry, that's just still the, I forget a piece. Hold on a second. So that was that 3 plus that 3. Okay, good. That was that 6. Hold on, let me back up. That plus 3a e to the 3t. Another 3a e to the t times t squared plus 6a. I got another 6a, but I needed a, no, hold on. Trying to do too much in my head. So let me write them out. I just want to make sure I don't lose anything. So there's a 3t squared a e to the t plus another 3a e to the t squared plus 6a e to the t times t. This piece gives me another 3a e to the t squared plus 6a e to the t times t, and then that gives me a 6a e to the t plus 6at e to the t. So when I combine all that, let's just make sure. I have 3, 6, 9 t squared e to the t. The t bits, I've got 12, 18 t e to the t, and then 6a e to the t. So that was just my third derivative. Oh, good Lord. So my second derivative, I need to multiply that by 3. So I'm going to get minus 3 at cubed e to the t. That's that. these are the same. So I got 6 of those times 3 is 18. So minus 18 t squared e to the t. And then this one I have 3, so minus 18 a t e to the t. All right, so that was my second derivative. My first derivative, 3 of those. So plus 3at cubed e to the t plus 9 t squared e to the t. And then I need to subtract y. Oh yeah, no, we're good. So that's minus a e to the t. No, minus a t cubed e to the t. Okay, so put that all together. And this is when you go, Jesus Christ, this was an easy one. This is just 4 e to the t. Well, you can see how the algebra gets kind of gnarly. But all this first stuff cancels. Yay. The second column cancels. Yay. Third column cancels. Yay. So we're left with 6a e to the t has to equal 4 e to the t. So a is 2/3. Okay. So now I think we're ready to write our solution. So we've got y equals c1 e to the t plus c2 t e to the t plus c3 t squared e to the t. So those were our fundamental set. And then our particular solution is now plus 2/3. And I know I've subsequently erased it, but that was a t cubed times e to the t. All right, so the moral of the story here is that we're doing the same process. It's just going to take us longer, right? We're going to have to go a little bit further because we have to find more derivatives of our guess. And this one was nice, right? I mean, it was just a single term. Let's at least get another one set up. We won't go all the way through it. But let's at least get it set up so you can see kind of really how bad this can get. And this one's still not terrible. So we'll stick to third derivative because I really don't feel like trying to do this much bigger. So let's take a third derivative minus 4 times the first derivative. And that's going to equal t plus 3 cosine of t plus e to the minus 2t. So just like always, let's start by finding the solution to the homogeneous because we're going to need it anyway, and we want to make sure that it doesn't match any of the things that we're going to guess. So as a polynomial, this will be r cubed minus 4r, which is r times r squared minus 4, which is r times r minus 2, r plus 2. So in terms of the fundamental set, we have 1 e to the 2t and e to the minus 2t. All right, so let's build our guess. So the guess for our particular, let's start with, we've got a polynomial. We've got a t, that's linear. So that suggests that we want an a plus bt. However, one of those is in the fundamental set, right? Remember the first thing we found was 1. Well, 1 is this piece. So that means we need to multiply by t. So that'll be our guess for that piece. All right, so then we go to the cosine. Well, cosine tells me that I need sine and cosine. So we'll have c times cosine of t plus d times sine of t. So that's going to take care of the part. Okay, so now let's go to the e to the minus 2t. So again, this is going to suggest that I want an e, big E, times e to the minus 2t. But again, e to the minus 2t is in my fundamental set. So I need to multiply that by t. So this one, I've got 5 unknowns. Oh joy. We're going to have to go down to the third derivative, equate everything so that we can find out what all those different values are. But I will leave this to you. So we'll just do the little ellipses there. If you go through all this, you should find that your particular solution is minus 1/8 t squared. So you'll find out that the a is 0 and b is minus 1/8. You're going to get a minus 3/5 sine of t. So d ends up being minus 3/5 and c is 0. And then lastly, you get a plus 1/8 t e to the minus 2t. So e will end up being 1/8. Okay. So good news, bad news time. We'll start with the bad news. The bad news is the algebra here sucks. Tons of it. We have lots of unknowns, a lot of things we got to find. That sucks. Okay, that's the bad news. The good news, we can do it. And we can do it exactly the same way that we already did for the second orders. So that is actually really good news to a mathematician, right? Mathematician, the algebra is algebra. I'll slug through it. But the can or cannot, we can. And not only can we can do it the same way. That actually earns a double thumbs up, right? So I know you're not going to like these. I haven't put these homeworks up because you're still working on the 8 stuff from chapter 8. I will go nice on you, I promise. Like this bit from Undetermined Coefficient, expect like maybe 4, maybe, right? Because I know the algebra is rough, but for sure practice building your generic, because without that you're sunk, right? And this whole repeated root and matching things that we already have is way more prevalent in the higher order, just because there are more roots in the higher order, so you're more likely to catch one that you already have. And it's also way more likely that there's repetition of one that you already have. Okay, so just watch out for that. All right. So I think at this point, we're going to call it a day. We've definitely beat our brains into this enough. So just so you know where we're going to be and what's going to happen. So on Friday, we're going to start looking at variation of parameters. How does that change? We're not going to really talk about reduction of order, because reduction of order, it's exactly the same process. But variation of parameters requires a little bit of a tweak. And so we'll look at that. We'll see how it's related to what we did for second order. I'll give you a hint. It's almost identical. Just bigger, right? Instead of having the 2x2 Wronskian matrix, we have the n×n, Wronskian matrix. But obviously, we're gonna have to look at that a bit, because one of the things we did, even though we didn't talk about it, was we found the inverse of that Wronskian. I don't know if you caught that when we went through the derivation, but along the way, we really did find the inverse. Well, finding the inverse of an n×n, not easy, right? So, but we'll talk about that on Friday. And then we're into the last week and we're cruising along. Okay. So I guess with that, unless you guys have anything else you need to share, have an awesome couple of days, and I will see you all on Friday. Except for Ian, who I'll see in half an hour, hopefully.
Exactly, half an hour.
All right. All right. I'll see you guys later. Have a good one.